Namaste everyone. Welcome back to the second PUC physics class, that is moving charges and magnetism. So in the last class we have discussed about the torque acting on the rectangular loop. Before that we have discussed about Biot-Savart's law. While discussing about Biot-Savart's law, we have derived an expression for magnetic field due to a circular coil at a distance x from the center of the coil. Magnetic field at a point P along the axis due to the current carrying coil, and the expression for B is equal to mu naught by 2 I into r square divided by x square plus r square to the power 3 by 2. So, this is the expression for magnetic field along the axis at a point P or at a distance x from the center of the coil. So, B is equal to mu naught by 2 I into r square divided by x square plus r square to the power 3 by 2. If x is very much greater than r, what is r? R is the radius of the coil and x is the distance from the center of the coil to the point P. If x is very much greater than r radius, then in that case magnetic field B is equal to mu naught by 2 I into r square divided by x is very much greater than r. So, in this expression we can neglect r because r is very less compared to x. So, we can neglect r. So, on neglecting r we get x square. It is approximately is equal to 0. R is approximately is equal to 0 compared to x. So, x square plus 0 whole to the power 3 by 2. So, B is equal to mu naught by 2 I into r square divided by x to the power 2 whole to the power 3 by 2. 2 cancels, we get x cube. This is only when x is very much greater than r. So, from this expression let us multiply both numerator and denominator by 2 pi. On multiplying 2 pi we get B is equal to, or multiply by 2 pi on both, that is numerator as well as denominator. So, B is equal to mu naught by 2 I r square divided by x cube into 2 pi divided by 2 pi, multiplying and dividing by 2 pi. So, B is equal to mu naught divided by 2 pi into 2, 4 pi into I pi r square into 2, right, 2I pi r square, 2I pi r square divided by x cube. So, B is equal to mu naught by 4 pi 2 I pi into r square. What do you mean by pi into r square? Pi r square is the area of the circle. So, pi r square is nothing but area A divided by x cube. So, B is equal to mu naught by 4 pi 2 into I into A. We know that the product of current and the area is nothing but magnetic moment M. So, magnetic moment M is equal to I into A. magnetic moment M is the product of current and area vector. So, M vector is equal to I into A vector, and also A vector is always perpendicular to the plane. A vector is perpendicular to the plane, therefore, magnetic moment is also perpendicular to the plane. So, I into A is nothing but M. So, B is equal to mu naught by 4 pi 2 M, I into A is M, 2 M divided by x cube. In vector form, B vector is equal to mu naught by 4 pi 2 into M vector divided by x cube. That is, this is the expression for magnetic field along the axis. Magnetic field B is equal to mu naught by 4 pi 2 M divided by x cube. Magnetic field in terms of magnetic moment. This is the relation between magnetic field and magnetic moment. Okay. B is a vector quantity, magnetic moment M is also a vector quantity, and also they both lie in the same direction. M is perpendicular to the plane, B is also perpendicular to the plane. If magnetic moment is into the plane, then magnetic field is also into the plane. If magnetic moment is out of the plane, then magnetic field is also out of the plane. So, this is the relation between magnetic moment and magnetic field. Similar to this, we have the relation between electric field and electric dipole moment. In the first chapter, we have derived one expression, that is E is equal to 1 by 4 pi epsilon naught 2 p by r cube. This is the relation between electric field and the electric dipole moment. In this expression, P is electric dipole moment, E is electric field. Here, B is magnetic field and M is the magnetic moment. Both the equations are similar. So, electric field, this is the expression for electric field along the axial line. Similar to this, we have electric field on the equatorial plane. The expression for electric field in terms of electric dipole moment on the equatorial plane, E is equal to minus 1 by 4 pi epsilon naught p by r cube. So, this is the expression for electric field in terms of electric dipole moment on the equatorial plane, right, electric field. So, the expression for magnetic field on the equatorial plane is, let us see what is the expression for magnetic field in terms of magnetic moment on the equatorial plane. So, on the equatorial plane, B vector is equal to, or it is approximately is equal to mu naught by 4 pi M by x cube. This is the expression for magnetic field on the equatorial plane. Relation between magnetic field and magnetic moment. So, if magnetic moment both are perpendicular to the plane, right, magnetic moment and magnetic field, they are perpendicular to the plane in which the coil is carrying current, and also they both lie in the same direction. If magnetic moment is into the plane, magnetic field is also into the plane. If magnetic moment is out of the plane, then magnetic field is also out of the plane. Okay. So, M is the magnetic moment and it is a product of current I and area vector A. So, M is equal to I into A. Now, let us see what is the SI unit of magnetic moment. SI unit of current is ampere, SI unit of area is meter square. So, ampere meter square is the SI unit of magnetic moment M. If there is a coil in which the current is flowing in clockwise direction, you just consider one coil So, in this coil the current is flowing in clockwise direction. So, this is the clockwise direction, right. So, the phase of the coil in which the current flows in clockwise direction is considered as, we know that when current flows through the coil, magnetic field is generated around the space. So, this coil is considered as, or the phase of the coil in which the current flows in clockwise direction is considered as magnetic south pole. The coil or the phase of the coil in which the current flows in clockwise direction is considered as magnetic south pole. Similarly, the phase of the coil in which current flows in anti-clockwise direction, this is when the current flows in clockwise direction. If the current flows in anti-clockwise direction, then the phase of the coil is considered as the north pole. Okay? The phase of the coil in which the current flows in anti-clockwise direction is considered as magnetic north pole. The phase in which the current flows in the clockwise direction is considered as magnetic south pole. Okay? If the current flows in clockwise direction, then always remember the magnetic moment is into the plane. If current flows in the clockwise direction in a coil, then the magnetic moment is always into the plane. Okay? If magnetic moment is into the plane, then that means magnetic field is also into the plane. They are directly proportional. If in a coil the current flows in anti-clockwise direction, then the magnetic moment is out of the plane. If magnetic moment is out of the plane, then that means the magnetic field is also out of the plane. Now, let us derive an expression for magnetic moment of electron revolving around the nucleus, and the value of Bohr magneton. Let us derive the expression for magnetic moment of electron which is revolving around the nucleus, and also let us find out the value of Bohr magneton. We know that the magnetic moment is the product of current and area. So, let us consider one electron which is revolving around the nucleus. So, this is the nucleus. We know that nucleus is the central part. Inside the nucleus we have protons and neutrons. So, charge of the nucleus is represented as Ze plus Ze, right. So, this is the charge of the nucleus. Nucleus is positively charged because of protons. Around the nucleus we have different orbits, and in those orbits electrons are revolving around the nucleus. So, consider one electron. Electron is a negatively charged particle. So, this is one electron, and this electron is revolving around this nucleus. So, it is moving like this in anti-clockwise direction. We know that the motion of electrons and the direction of current, they are opposite to each other. If electron is moving in this direction, then that means the current is in the opposite direction. That is, this is the direction of current and this is the direction of motion of electron. So, this is considered as a coil. Okay? So, this is considered as a coil. So, this is the direction of current I and this is the motion of electron, that is, this is the direction of V. V is nothing but the velocity or the speed. This is the direction of motion, right. Here this is the direction of velocity, here this is the direction of velocity, here this is the direction of velocity. And R is the radius, right. R is the radius, V is the speed, and I is the current flowing through the coil. Here it is considered as a coil. I is the current and the current is flowing in clockwise direction. We know that if current is flowing in clockwise direction, then the magnetic moment is always into the plane, right. Magnetic moment is into the plane if current is flowing in clockwise direction. Magnetic moment is into the plane means it is represented by a cross. Magnetic moment is into the plane, so mu. Here the magnetic moment of electron is represented by mu L. Always remember, magnetic moment of electron is represented by mu L and it is into the plane. That is why here we have cross mark, it is a vector quantity, so mu L vector, right. So, consider an electron, E, which is revolving around the nucleus with the speed v. Let I be the current flowing in clockwise direction and magnetic moment is into the plane. Magnetic moment is into the plane. So, this is the direction of current. So, current is flowing in this direction. We can use right hand rule. If the curled fingers give the direction of current, then the thumb gives the direction of magnetic field. Here the current is flowing like this, therefore, the thumb is in this direction, it is inwards, that is magnetic field is into the plane. So, this is the direction of current and thumb gives the direction of magnetic field which is inwards, therefore, magnetic field is into the plane, that means magnetic moment mu L is also into the plane. So, magnetic moment is into the plane and it is represented by mu L. We know that current I is equal to Q by T. Rate of flow of charge is nothing but current. Here Q is nothing but electron. So, I is equal to E divided by, Let us consider T. I is equal to E by T. E is nothing but charge of an electron. What is T? T is the period of revolution of electron. What do you mean by period of revolution? It is the time for one revolution around the nucleus. Time for one revolution around the nucleus is called as time period, and it is represented by capital letter T. So, I is equal to E by T. Now, let us see what is the expression for T. We know that speed is equal to distance by time, or time is equal to distance by speed. Time is equal to distance by speed. Time is T, time period T. Time period T is equal to, time for one revolution is time period T, which is equal to, when this electron completes one revolution, what is the distance covered by the electron? So, this is the distance covered by the electron, which is nothing but the circumference of the circle. So, during one revolution, the distance covered by the electron is 2 pi r. 2 pi r is circumference of the circle. Here r is the radius. So, 2 pi r is the distance divided by speed. V is the speed. With this much speed, the electron covers this much distance. So, time period T is equal to 2 pi r divided by speed. Speed is nothing but V. Therefore, I is equal to, current I is equal to, here I will write, I is equal to E divided by T. T is 2 pi r divided by V. I is equal to EV divided by 2 pi r. This is the expression for current in terms of speed and orbital radius. Okay? EV divided by 2 pi r. We know that the magnetic moment is usually represented by m, but magnetic moment of electron is represented by mu L. So, magnetic moment mu L is equal to I into A. So, the magnetic moment, general expression for magnetic moment is current into area. Here mu L is equal to, current is EV divided by 2 pi r into area, right. So, magnetic moment mu L is equal to E into V divided by 2 pi r into area. Area of the circle is nothing but pi r square. So, A is equal to pi r square. So, magnetic moment of electron mu L is equal to pi cancels, r cancels, we get EVR divided by 2. Now, let us multiply above equation by mass of the electron me. Me is nothing but mass of an electron, and what is the value of me? Always mass of the electron is 9.1 into 10 to the power minus 31 kg. So, multiply by me, mu L is equal to EVR into me. Me is nothing but mass of electron divided by 2 into me. So, mu L is equal to EVR into me. Me V R into E, same equation, divided by 2me. We know that mvr is nothing but the angular momentum of electron. This is nothing but the angular momentum. What do you mean by angular momentum? Moment of momentum is called angular momentum. In circular motion we have angular momentum, and in linear motion we have linear momentum. Angular momentum is represented by L, and it is the cross product of R and linear momentum, or L is equal to Rp sin theta. A cross B is equal to AB sin theta. Here we have R cross P. So, R cross P is nothing but R, the angle between R and P. What is P? P is the linear momentum, or linear momentum P is equal to, it is a product of mass and velocity. So, on substituting we get L is equal to R, P is nothing but m into V sin theta. Theta is the angle between R and P, right. If angle between R and P, or it is angle between R and V, P is equal to m into V, P is a vector quantity. So, P vector is equal to m into V vector. Velocity, direction of velocity and linear momentum, they are same. So, R into P sin theta, here R m V sin theta. Theta is the angle between R and P, or it is angle between R and V. Okay. If theta is equal to 90 degree, let us see what is the angle between R and V. Here this is the direction of V and this is R. Angle between them is 90 degree. Here this is V, this is R, angle is 90 degree. So, at every point angle between R and V is 90 degree. So, theta is 90, sin 90 is 1, I get L is equal to mVr. Therefore, mVr is nothing but the angular momentum L. Here we have mVr into E. So, mVr is nothing but L, E into L. E into mVr is nothing but L, angular momentum, divided by 2 into me. Me is mass of the electron. So, that is the expression for magnetic moment of electron in terms of angular momentum. That is, mu L is equal to E into L divided by 2 me. Mu L is a vector quantity, angular momentum is also a vector. Mu L is equal to E into L divided by 2 into me. Mu L by L, the ratio of magnetic moment of electron and the angular momentum, that is mu L by L is equal to, mu L by L is equal to, we get E by 2me. E is charge of electron. What is the value of E? 1.6 into 10 to the power minus 19 divided by 2 into mass of the electron is 9.1 into 10 to the power minus 31. So, the ratio of magnetic moment of electron and the angular momentum is 1.6 into 10 to the power minus 19 divided by 2 into 9.1 into 10 to the power minus 31. This ratio is called as gyromagnetic ratio. The ratio of magnetic moment of electron and the angular momentum is called gyromagnetic ratio. So, we have gyromagnetic ratio. Gyromagnetic ratio is constant and its value is 8.8 into 10 to the power 10 coulomb per kg. Its value is 8.8 into 10 to the power plus 10 coulomb per kg. This is the value of gyromagnetic ratio. What do you mean by gyromagnetic ratio? It is the ratio of magnetic moment of electron and angular momentum. Is called gyromagnetic ratio. And the value of gyromagnetic ratio is 8.8 into 10 to the power 10 coulomb per kg. So, mu L by L is gyromagnetic ratio. So, from this expression, I will consider this expression now. Mu L is equal to E into L divided by 2me, right. Mu L is equal to E into L divided by 2me. L is the angular momentum. According to Bohr's postulates, we have 3 postulates. And according to the second postulate, we know that the angular momentum of the stationary orbit L is equal to, it is the integral multiple of h by 2 pi. Or in other words, we can also say that the stationary orbits are those for which the angular momentum L is the integral multiple of h by 2 pi, right. So, L is equal to nh by 2 pi. Mu L is equal to E into L is n into h divided by 2 pi into 2me. According to Bohr's postulate, we have L is equal to nh by 2 pi. Here, let us substitute for L. L is nh by 2 pi into 2me. So, magnetic moment of electron mu L is equal to E n h divided by 2 into 2, 4 pi m into E. E n h divided by 4 pi m into E. Okay. N is an integer. N is equal to 1 for the innermost orbit, right. For the innermost orbit, n is equal to 1. When n is equal to 1, mu L is equal to E into h divided by 4 pi m into E. This is only when n is equal to 1. When n is equal to 1, for the innermost orbit, we have n is equal to 1. Okay. So, the magnetic moment of the innermost orbit is called as Bohr magneton. Magnetic moment of the innermost orbit of hydrogen atom. Magnetic moment of the innermost orbit of hydrogen atom is called as Bohr magneton. Bohr magneton is the magnetic moment of the innermost orbit of hydrogen atom. The magnetic moment of the innermost orbit of hydrogen atom is called Bohr magneton. It is also a constant because E is a constant. We know the value of E, 1.6 into 10 to the power minus 19 into h. H is Planck's constant, 6.63 into 10 to the power minus 34 divided by 4 into pi is a constant and its value is 3.14 into mass of the electron is 9.1 into 10 to the power minus 31. On substituting all the values, we get Bohr magneton mu L is equal to 9.27 into 10 to the power minus 24. 9.27 into 10 to the power minus 24. What is the SI unit of magnetic moment? Ampere meter square. So, this is the value of Bohr magneton, 9.27 into 10 to the power minus 24. In vector notation, we know that mu L vector is equal to E into L vector divided by 2 into ME. Okay? If E is charge of the electron is always minus 1.6 into 10 to the power minus 19. Here negative sign indicates that the direction of angular momentum and the magnetic moment are opposite to each other. Negative sign indicates that the direction of angular momentum and the direction of magnetic moment of electron both are in opposite direction. That is, we know that the magnetic moment is into the plane because magnetic field is into the plane. So, this is the direction of magnetic moment. Let us see what is the direction of angular momentum. So, this is the direction of V or P, this is the direction of R. We know that L vector is equal to R cross P vector. L vector is equal to R vector cross P vector. That is, L is always perpendicular to the plane which contains R and P. So, this is the direction of P, this is the direction of R. That means angular momentum is perpendicular to both V and R. That is, this is the direction of L. Always angular momentum is perpendicular to the plane containing R vector and P vector. Therefore, angular momentum is like this. It is out of the plane, magnetic moment is into the plane. So, negative sign indicates that the angular momentum is opposite to the magnetic moment. So, magnetic moment is into the plane, angular momentum is perpendicular to the plane containing R and V. So, it is like this. This is the direction of L and this is the direction of mu L. Okay. This is about the magnetic moment of electron which is revolving around the nucleus and the value of Bohr magneton. Okay. Magnetic moment of electron is always represented by mu L. What is Bohr magneton? It is the ratio or it is the magnetic moment of the innermost orbit of hydrogen atom. Magnetic moment of innermost orbit of the hydrogen atom is called as Bohr magneton, and the ratio of magnetic moment of electron and the angular momentum is called gyromagnetic ratio.